Hey up me ducks, Physics PhD live here, and I would like to welcome you to the first of these, my Maths and Sciences tutorials. And in this very first lesson, we're going to be having a look at some algebra. We're going to be seeing what we mean when we're talking about things algebraically. We're going to explore the ideas of constants and variables, and we're going to use this to actually explore one of our first equations that we're going to encounter when we deal with any kind of maths or science. So first and foremost, what do we mean when we're discussing things algebraically? Normally, and for the context of this lesson, we're going to be thinking about this as allowing letters to replace, which I'm going to say in big inverted commas, to replace numbers. Now, there's a big advantage to this. That being, it makes it easy to retool one equation for many different situations. And we'll see an example of this today as well, what I mean by this. So basically, it allows us to say, these letters here, I don't need to necessarily know what they are right now. I can find them out if I'd like, but this is just giving me the explicit relationships between these values or these things of interest. So, let's actually get to the bones of how we can work with these letters. So, they work essentially the same as numbers. And again, as normal numbers, and I'll put normal in, again, big inverted commas there. So that being that we can add them. In fact, let's not do that. Let's do a big bullet point. So we can add them. So we can say that A plus A is the same as having two lots of A. So that's equal to 2 times A is equal to... Okay, I've realized that my A and my 2 look quite similar there. So in fact, allow me to just erase that for simplicity's sake. So let's go for a different letter. I've just realized that's probably not going to make things very helpful. So let's go with instead, let's go with B. So we have B plus B is equal to 2 times B. And algebraically, we're allowed to simplify this, just read as 2B. Or not 2B? That is the question. Where are my Shakespearean friends at? We can subtract them in the same way we have here. So we can have, say, 2B minus B is equal to, and I'm going to write this out really explicitly as well so we can see how it comes about, is equal to, I'm going to pick up the 2 times the B here, so I've got 2 times B minus 1 times B. And what I can do is I can actually find everything that includes a B, and I'm going to put it over here. And then I'm going to pick up in a bracket everything that acts onto a B, and I'm going to put it into another bracket, so that being 2 minus 1 times B. And then I can solve this bracket here. So 2 minus 1 we know is equal to 1. So then this is equal to 1 times B, or is just equal to B. What else can we do? We can also multiply. So if we have two different terms, so if we have a times b, this just reads as equal to ab. Or we can also have b times b. And this just gets simplified nicely to b squared, or b to the power of 2. And of course, if we can multiply, we can also divide them. So we can have, say for instance, 3b divided by b is going to be equal to, and again I'm going to split this up, 3 times b divided by b. Now hopefully we can all remember from primary school, from elementary school or whatever you call it, that anything divided by itself is always 1. So therefore this is equal to 3 times 1. Now we can do loads of other things as well with these letters, but this is a nice place to start, and hopefully it shows us that it's very simple to work with letters instead of numbers, as we follow the exact same rules, and as long as we're consistent, then everything works out well. So, given that these are rules that we can play with, one of the things that we're often asked to do in an introductory algebraic class is to collect like terms. And so this just means, that the goal of the game is to find things of the same power so when I say of the same power, I mean in the context of what we have upstairs here, and letter, which again I'm going to put in big inverted commas, because sometimes we'll have regular old numbers as well as our letters mixed together, but we'll see an example of that shortly. So let's go, so now that this is our goal, well, okay, so we found them, and then we want to lump together neatly. That's not how you write an N. There we go, that is. And then we want to lump them together neatly for tidiness sake, because everything looks better when it's tidy, right? Okay, so let's start with a nice simple form of this then. Let's have some amounts of x and y, as we tend to use x and y a lot. So let's say that we have 3x plus y minus x plus 2y. And again, the game is to collect like terms here, so we want to bring everything together. So I'm going to start with the x's, so I find that I have an amount of 3x here and an amount of negative x here. So I have 3x minus x. Okay, good. And now I'm going to look for everything that has a y in it, because that's the only other thing I found which exists in this expression. So I have a positive y and a positive 2y. And so let's include that. So I have plus y plus 2y. And I've now changed the colors as well, so that we can see even more profoundly the differences between them. So, using the rules that we've established upstairs here, I now know that I can add all of these guys, and I can subtract them if needs be. And so I'm going to apply those rules, and so then this is going to be equal to 2x plus 3y. And hopefully you can see how and why it is that I've done this. Let's do one more example, which is going to be a lot more complicated than this one, but just to show what the name of the game is. And we're also going to turn this into an equation. Actually, no, we're not. We'll still keep it as just an expression. So let's go with 2x to the power of 2 plus 3x minus 2y plus y minus x plus 7. And this is just an ordinary, plain old simple 7 hanging out over here. So, let's play our game then that we did before. So I'm going to need 3 colours this time. So, I remember that in my brief for the game, I told myself they have to be of the same power. So, I note that there's only one of these guys here which has a power involved, and that happens to be this term here, which is a power of x squared. And I don't see anything else along my line which includes any powers. So this friend over here is completely alone. So I just have 2x squared as before. Okay, and now I'm going to pick up x's. So I have a positive 3x here and a negative x here. So I bring them together, so I have plus 3x minus x. And now I'm going to go and hunt for some other terms. So I have minus 2y and positive y here. Those are my y terms. So minus 2y, positive y, and then finally, whatever colour this is going to turn out to be, I have an ordinary old number. Well, that's a really cool colour, actually. Plus 7. Whoa. That's intense. Okay, so let's simplify each of these things which is of a similar colour. So I have just 2x squared. And then 3x minus x is 2x. Minus 2y plus y is negative y. And then the 7 is just 7, unsurprisingly enough. That's a really cool color effect I've got going on there. I like that. Okay, so we see that we can use the rules above to play the game, and that allows us to create these kind of expressions, which we're then able to simplify. So there's loads of more, complicated ways that you can organize these guys together to force you to have to do multiplication and division. But that is more just an exercise for thoroughness, and you don't really learn anything new from it. You just become better at this. And I'm of the opinion that a lot of you will be wanting to either pick up new skills, and if you're wanting to get better, then I can provide you with resources to do so. This is more just meant to be the background on it. Okay, so let's now talk about... there's my pen again. Let's now put a line in the sand. And let's now talk about constants and variables, as these are the two main ways that we're going to be dealing with letters when we're using them in our equations, our functions, our expressions, our everything. So constants, we typically will denote with an A, a B, a C, a K, M, this sort of thing, and a variable will typically have as, say, X, Y, Z, T, for instance. So, the point of a constant is it's fixed for that given iteration, for the given situation we're looking at, and will often depend on some physics, if we're talking about a physical system. So, for instance, this could be mass. If you have some sort of situation in which you have a ball which is falling under gravity, apparently at a fun angle, then it's going to be of a constant mass m, you assume. So that would be one instance in which you're using your constant m. Whereas a variable allowed to vary, hence its name, across a range. Now I'm going to put that in big, bold letters, as we're going to meet this word here a lot, and with good reason. But This is what we like to call a spoiler. Okay, so it's allowed to vary across a range, and you'll typically, in, say, a scientific experiment, have, say, things like a control variable and an independent variable. Sorry, not independent, a dependent variable. Don't know what I'm talking about there. So yeah, you'll have a control variable and a dependent variable. So this could be, for instance, you're wanting to do an experiment where you want to induce a current by applying a magnetic field across a wire. So your control variable is the one that you're varying, and in this case it will be the magnetic field strength H, and the thing that you're wanting to measure, which is your dependent variable in the experiment, will be the current I, and you're wanting to see how the current I depends on the thing that you're controlling, H. Sorry, no, I've been so foolish with this. Ignore what I've just said in terms of that. It's not. This isn't a control variable. This is the independent variable. And now it's coming out of the woodwork that I actually don't do experiments myself, but rather I am a theoretician. I do apologize. But yeah, in any case, the spirit of what we're getting at here is these are variables in the sense that we're wanting to see how one of them will influence another. So that being how the magnetic field will be affecting the current that we're inducing in this particular instance. Right, okay, so let's meet our first equation which makes use of, which makes use of constants and variables as we've just met them. And many of you will have seen this and met this before, but I'm still going to write it out, for it deserves a grand entrance, and that being y is equal to mx plus, anyone want to guess? C. Okay, so let's have a look at what's going on here. So let's first and foremost identify our variables, so the things that we're going to allow ourselves to vary. We're going to allow ourselves to vary this value of y here and of this value x here. The things that we're going to hold constant for each iteration of this equation here are going to be this m and this c, and we'll see what function's a bad word to use there, what role these guys here play in this equation. So let's get ourselves started on this, and as we've just identified with constants, let's hold m and c to be a fixed value for this. So let's start off with a nice simple one. Let's make m equal 1, c equal 0. Okay, and then given this, what we're now going to do is we're going to do a list of values for x, and then we're going to see what y will be as a consequence. So that is to say, we're going to vary x across some given range, and we're going to see how y varies as a consequence of x changing its value. So let's go between -2 and +2. As this way we get to see how it behaves at 0, the origin, with negative numbers and also with positive numbers. So, to calculate this, what we need to do is simply plug in our values of x, m, and c, and we read off what y is going to be. And so in this instance here, let's do this in red, we're going to have, for when x is 2, so y at -2 is going to be equal to 1 times -2 plus 0. Any guesses for that? It's -2. And so let's write that in. And so let's do it again for y of -1 is equal to 1 times minus 1 plus 0 is equal to minus 1. And for when x is equal to 0, so y of 0 is equal to 1 times 0 plus 0 is equal to, you guessed it, 0. Beautiful. And so we should start to see a pattern emerging here. And indeed, what we're doing is we're simply just counting up in ones. And what we'll notice that we count, in fact, more than just that. In this instance here, we're counting up in amounts of m. And we'll see that becoming more specific when we do another example. So let's fill in these values here. And now to really see what this behavior is doing, we're going to graph what this y and this x look like. So when you draw an axes, always give them arrows to indicate in which direction they're increasing, and also, please label them. Always do this. An unlabeled axis is a very sad thing. Okay, and then let's identify as well the points on the x-axis that we're interested in, that we've got points for. So we have minus 2, we've got 1, we've got the origin, 0, 1, and positive 2. Okay, so when x is minus 2, y is also minus 2, which is way down here. When x is minus 1, y is minus 1, which is way here. When x is 0 at the origin, y is also 0 over here. X is 1, y is 1. And then finally, x is 2, y is 2. Now, what we notice about this, unsurprisingly, is it makes a straight line. If I could, draw freehand, but apparently I can't. Life's tough. That's too bad. This shouldn't surprise us, because this is indeed the equation, and this is my shorthand way of writing equation, of a straight line. Okay, so this is how we can take variables y and x with constants m and c and create what is essentially a function of x. This function here is a straight line. This is one way of using this language here. I'm going to stick with this convention for the time being, but I will also change into a notation which reads out, I'm just going to write it in blue up here, the function of x is equal to this business down here. So don't be afraid, and I will give you plenty of warning when we move over to this notation, but these two here can be interchanged within reason. Okay, beautiful. So we said before as well that with constants we can change them for each iteration. So let's change our constants around and recalculate how y varies because of x. So let's again write down our friendly line equation. So y is equal to mx plus c. And this time let's pick m is equal to minus 5 and c is equal to 5. Okay, so these ought to be sufficiently different from the first iteration, and so once again, let's write out a table of how y and x are related to one another. So we have x, y, and let's go with the same range we had with x again, so minus 2, minus 1, 0, 1, and 2. Amazing. Now, this is going to be a little bit more involved, so again, let's be careful here. So y when x is minus 2 is going to be equal to minus 5 times by minus 2 plus 5. Okay? In fact, actually, one sec. I don't like how this is going to look, so allow me to just in fact, alter this a little bit. I'm going to instead make c equal to minus 5 as well. So I now have this minus 5. The reason being this makes it a little bit more interesting. Okay, so minus 5 times 2 times minus 2 is equal to 10. 10 minus 5 is equal to 5. Y of minus 1 is equal to minus 5 times by minus 1. Minus 5 is equal to, this guy here comes out to be equal to 5. 5 minus 5, 0. Easy days. Y of 0 is equal to minus 5 times 0. Minus 5 is minus 5. Y of 1 is equal to minus 5 times 1. Minus 5 is equal to minus 10. And as before, we find ourselves moving in increments of m. This shouldn't surprise us because of the way that we've written this down. This is the scaling factor for how x interacts with y. So this scales x. So let's write our values in here then. So we have 5, 0, minus 5, minus 10, and then ultimately it's going to be minus 15. Okie dokie. So let's plot our axes, and we're going to need quite a lot of negative in the y and only a little bit of positive in the y. Yeah, there's a lot of negative y's. What can you do about it? And again, arrows on axes, always do this, please, 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 I beg of you. And then let's write on our values of x that we're going to go between, so minus 2, minus 1, the origin where all things begin, 1, and 2. Amazing. Okay, so when x is minus 2, y is equal to 5, which is all the way upstairs here. When x is equal to minus 1, y is equal to 0, which is on the x-axis, because when y is 0, we cross the x-axis. This becomes very important later on. When x is 0, y is equal to minus 5, which is down here. When x is 1, y is equal to minus 10, which is down here. And when x is 2, y is minus 15, which is down here. And again, we can allow these guys to form our straight line, which I still can't draw freehand. Life is terrible. What are you going to do about it? Okay. So let's compare and contrast for just a hot second here. And so, oh, no. Okay, so let's compare and contrast for just a hot second here what we have. So we have two lines that we've created, one of which is going uphill over here, and the other of which is going downhill over here. In the first instance, we note that we're going uphill in ones. And here we're going downhill in fives. Amazing. What else do we notice? We notice that we cross this axis here, the y-axis, at the origin at x equals 0. No, yes, at x equals 0, obviously, because that's where we have the intercept, but also at y is equal to 0. Amazing. And in this instance, we cross the y-axis at... No, we... Yes, we cross the... of course... We cross the y-axis when y is equal to minus 5. Sorry, I wanted to be sure I was saying that correctly. We cross the y-axis when y is equal to minus 5. Amazing. Okay, so what's the justification for this? Well, unsurprisingly enough, it is all encoded in these constants here, the m and the c. So in the context of our straight line graphs that we've just been playing with, then we find that x and c have, we find that x and c have some very specific purposes. Not x and c, m and c. We find that m is what we call the gradient. So that is, it tells us how steep. So that is to say, in what increments are we going up or down in? So in the first instance, we are going up in ones, and in the second, we are going down in fives. So we know how steep it is, and we also know in what direction. So again, in the first instance, we were going uphill, and in the second instance, we were going downhill. Okie dokie. And so, when we have this other constant c, this is what we call the y-intercept. And this tells us when we cross the y-axis. So basically, this pins precisely where the x being 0 value is going to be. So you can either move it up or you can move it down. This being where you have your x is equal to 0. And then your c either displaces the intercept up or down depending on its magnitude and sign. Okie dokie. So, let's quickly reflect then on what we've learned in today's session. So, we've learned how to collect like terms. We've learned what the differences are between variables and constants. And finally, we've met our first equation being y is equal to mx plus c. And this we're going to see a lot more of in various different incarnations, and every single time we meet it, we should be prepared to deal with it in a way that we've just done. Thank you very much for joining me for this first week of our tutorial in which we've met algebra, and I hope that you can join us this time next week to explore the wonderful world of solving equations that look like the one that we've just met. I've been your host, Physics PhD Life, and I'll speak to you soon.